What's going on, everybody? Today we're going to be talking about electric fields. Electric fields are an important concept in physics. They apply to a whole bunch of different subject fields in physics. You have gravitational fields, magnetic fields. They're all over the place and they permeate through all of space. On the most basic level, electric fields are defined as force per charge. And this gives you units of newtons per coulomb. That's the units of the electric field. It can also be expressed in volts per meter. If we substitute Coulomb's law into this expression, so Coulomb's law, we have Q naught Q1 divided by 4 pi epsilon naught r squared into the expression. We have an electric field of charge divided by 4 pi epsilon naught r squared. So this expression is just for like a single point charge, but you can expand it into different configurations of charges. So you can sum all the charges together, giving you an expression for different configurations of charges. 4 pi epsilon naught, your constant out front, divided by Q1 r squared plus Q2 r squared plus dot dot dot. So that would be a different configuration of charges when you have multiple charges together. We can also, as we'll see later, another important concept in fields is that they carry energy. So we have these different expressions. This can also apply to a continuous charge distribution, where instead of summing the charges, you now have the electric field defined as 1 over 4 pi epsilon naught delta Q over r squared. And that's for a continuous charge distribution on a certain surface of some sort. Next, we're talk about electric field lines. So electric field lines, they are good for visualizing electric fields, and that's why we use them. Electric field lines, let's say we have a positive charge. Electric field lines begin on positive charges and they terminate on negative charges. Sorry, that first one's pointing out. They terminate on negative charges. So you can help yourself visualize different charge distributions by these rules. They begin on positive charges and end on negative charges. Next we'll look at charge densities. So we can write our expression for the electric field as we have our constant out front, 1 over 4 pi epsilon naught, and we can integrate over a charge density dq over r squared. You can have different dimensional charge distributions. So in 1D, we have lambda equals charge divided by length, and this will give us dq as lambda dx, where dx is just an infinitesimal length. In 2D, use area with sigma equal to Q divided by area, which gives us dq as sigma ds. ds is just an infinitesimal area or surface area of a particular configuration, or if you have like a charge on the surface of a sphere or something like that. Then we have three-dimensional as rho equals charge divided by volume, which gives us dq as rho dv. So you can plug these dq's into a charge distribution and integrate over a particular distance, area, or volume, depending on what dimensional thing you have to solve for in the electric field. Next, we're going to look at something kind of cool. We have charge and the force of the electric field defined as F equals Q E an external electric field, which can also be defined from Newton's second law as NA. And this gives you A as Q E over F. And this is going to lead into, we're going to solve the angle for these charges moving in external electric fields. So from this we can obtain V as V naught plus Q E divided by N. Oh, I apologize. This is M divided by M, and QE divided by MT. And we can check this, gives the units of velocity. So we have right here is an acceleration meters per second squared. And by adding units of seconds on top, we have meters per second, which is velocity. Then we come around to get, we want to find the x and y components to get, if we have a charge traveling a length L in time t, we have the distance, or the x position, as v naught t equals L, or we have t equals L divided by V naught. We can also get the, we can also have the y component as y equals 1/2, and we take the y component of acceleration t squared. And this is going to give us, if we plug in our y component of acceleration, we have 1/2 Q E over N t squared. So we have our time t squared right here. And that, and then we can substitute in for t our L over V naught. So we get 1/2 Q E divided by M T L over V naught squared. So we can put this whole thing as L divided by V naught squared. So we've been finding these x and y components because we're trying to find the angle of a particular charge traveling in an external magnetic field. And this leads us to have the tangent of theta equal to, so now we have the y component of v and the x component of v, and we can plug these in. We have QE divided by m and L divided by V naught, all divided by, we have V naught on bottom. And this is going to give us QEL over m V naught squared. And that's the angle of the charge. And this is important because you want to find the angle, because in cathode ray tubes, which are used in TVs and computer displays and everything with a display on it, they use this concept in CRTs, cathode ray tubes, and you have a hot filament and a charge passes through two conducting plates, which gives it an x direction, and then it passes through two other conducting plates, which gives it a y direction, and it lands in this particular spot on a fluorescent screen. And so you have a hot filament which sends like a beam or a stream of electrons passing through these plates and giving the different directions on different positions on a fluorescent screen. And so this is kind of a very important concept to find these angles, because they're used in a whole bunch of different technologies and things of that nature. So those are the basics and fundamentals of electric fields. This was just a brief introduction of what the electric field is and a couple different concepts in this. I hope you can go out and have your curiosity sparked and go discover more about the electric field, because it's a very interesting thing. Maxwell's equations are based solely upon and all of electromagnetism for that matter, is based on finding the electric or magnetic field. And so if you like this video, give it a thumbs up, and I'll see you all next time.